Have you ever wondered how a few sloppy lines of code can wreak havoc on an entire system? Coming up, watch as I clumsily fumble my way through a buffer overflow exploit. Hang on. Yes! If you've written your first Hello World, then I think you're ready to join me for this, the buffer overflow nightmare.
It is not a virus, it's a worm.
And tomorrow, the code red worm is expected to cause another round of outages and slowdowns on the internet.
Experts have reason to worry. The first attack, July 19th, infected about 300,000 systems in 9 hours.
Code red internet worm is trying to crawl into a computer near you.
On July 13th, 2001, the code red worm began spreading rapidly, infecting web servers running Microsoft's Internet Information Services software, and it was exploiting a buffer overflow vulnerability. A buffer overflow is a type of software vulnerability that occurs when a program writes more data to a block of memory or buffer than it was allocated to hold. I thought it would be fun to have a go and demonstrate how a buffer overflow works. So on that note, let's get hacking. To identify a vulnerable application, we would take the following approach. So this is my file that I'm going to be using, and it does nothing really, just copies some data into memory. I'm going to compile it using the GCC input that you can see there, and now we've got an executable mainframe that we can run. So first, let's just run the program as is and provide a couple of bytes for input. So what's going to happen is the program will take those bytes, copy it into its buffer on the stack, and then return. And that's all good. But what about if we want to try to exploit a buffer overflow? So for this, I'm going to use a Python script to help me out. So we call it exploit main.py, and then you need to import the sys module, and that will allow us to write bytes to the standard out. So there we go, standard out.buffer.write, and then I'm going to write a series of hex 41 bytes, which is the capital A in ASCII, and I'll send that to standard out 2000 times. And now we can pipe that into our program. Well, first, let's just try the script, check it works, which of course it doesn't. Provide B there to tell it that we're treating it as bytes, and there we go, capital A, which is hex 41. So that's what we're going to send to our program with a view to trying to crash the program. If the program crashes, that means it's vulnerable. And there it is, a segmentation fault. So that means it's vulnerable. We've got a overflow condition. We now want to try and craft our Python script to try and figure out exactly how many bytes we need to cause the overflow to occur. So using GDB, which is the GNU debugger, we can inspect the stack when it crashes. But again, we really should have a working bit of Python. And there we go. I've jumped straight to the good stuff. So at 1038 bytes, we are able to see 41s. Subtracting that by 1, we've actually got not quite enough bytes into our stack pointer. You can see there I'm counting actually the number of bytes that are 0, and you can see when I used 38 bytes I did it basically nailed it. So putting that back to 38, we can run that and make a note that 1038 bytes is exactly where we want to be. Okay, and that looks good. And then just for good measure, if I go to 39, we can completely corrupt everything, and you'll see there that that's just nonsense again. So it really does seem like 1038 is the magic number. So I just did that, found that by trial and error. Okay, so injecting our payload. So I found these machine instructions online from some nefarious websites, and they're basically just assembly bytes, so they're executable code, which have been stored as bytes in a variable called shellcode. I'm adding that to my my standard output. So I've got a bunch of 41s, 1038 of them. I've got the shellcode, and then we've got a return address here. And for the time being, that's just going to be 6 bytes of return address. 51. So we'll easily be able to see that in our when our segmentation fault occurs. So now, because we actually need to reduce the number of x41s by the length of the shellcode and the length of the return address, otherwise we'll go too far, as demonstrated just previously. Because we basically need to always provide 1038 bytes for this to work. So you can see subtracting the shellcode and subtracting 6 times 5, which is 30. Again, jumping into the debugger, we will run our Python exploit code and see if we can see 51s now in the stack pointer. Perfect, so that's looking really good. Okay, so the NOP sled is the final piece of this puzzle, really. We need to exchange the initial buffer input from x41 to x90, which is a no operation. So first we run the program, and then we're going to inspect the memory at the beginning of the buffer, so 1000 bytes to the left. And you can see we've got all those 41s, which you'd expect. So if I just swap that out for 90, that's the no operation assembly instruction. And now have a look at the memory there. You can see we've got a load of 90s. This is all starting to get a bit complicated now, but we now have to come up with a return address to put in place of our 51s. So I'm going to go back to the start of the buffer, and that's the memory address near the start. So it was 1000 bytes left of this stack pointer. So we want to change that. So we're using little endian Intel addressing, so we have to put the addressing back to front. And then what this is going to basically do is our normal main program will run. It will copy in this bytes that we're providing into the buffer, and then it will return, well, it will think it's going to return to the main. It's actually going to return into here, into this bunch of 90s. Those are going to be executed now rather than just simply copied. And when our application executes them, it finally hits our shellcode. Hang on. Yes! So if you found this useful, I highly recommend you go and check out the computer file video on buffer overflows, because it massively helped me out. Thanks, guys. this made absolutely no sense, then I suggest you go and check out the computer file video on this subject, which was really useful and really helped me learn about this when I was trying to film this video.